In this chapter, we're going to be going over the derivative of the ln of x. So here's the derivative right here. The derivative of the ln of x, d dx of ln of x, equals 1 over x. So this is just one of those things that you're just going to have memorized going forward. The derivative of ln of x is 1 over x. So let's do a couple examples where we need to use that. First one, we have y is ln of x all raised to the 5th power. So this is going to be the general power rule first. So we're looking for dy dx, or y prime. It's going to be the derivative of the outside, which means you bring the exponent down out front, leave the inside alone, subtract 1 from the exponent, times the derivative of ln of x. The derivative of ln of x is 1 over x. So this gives us 5 ln of x to the 4th over x if we just clean it up a little bit, and that is good enough. Okay, next one we have y equals x times ln of x. So you should notice that this is going to be the product rule because we have two different factors with an x in them being multiplied, x times the ln of x. So this is going to be dy dx is going to be the first times the derivative of the second. The derivative of the ln of x is 1 over x, plus the second times the derivative of the first. The derivative of x is just 1. So this is going to be x times 1 over x cancels to 1. So it's 1 plus ln of x for the derivative. Okay, so those are just a couple examples using techniques that we've already have learned involving the ln of x. So now for the more general definition, that was just taking the derivative of ln of x. Now we're going to be taking the derivative of ln of some function g of x. So instead of an x as the input, it's going to be some other function. So the derivative here is going to actually be using the chain rule. When you do this using the chain rule, what you end up getting is the derivative is going to be g prime over g. So it's going to be the derivative of whatever this inside is divided by whatever that is. So I ignored everything else that I just have in that little box because that's kind of the important thing to know for this particular rule here. Okay, let's do a couple examples. First one, we want the derivative of ln of 2x plus 1. So notice that this one is not just the ln of x, it's the ln of 2x plus 1. So based on this rule, it's going to equal the dy dx is going to equal the derivative of what's inside divided by what's inside. So the derivative of 2x plus 1 is just 2. And we divide that by 2x plus 1. So g prime over g, 2 over 2x plus 1. And that's actually all we can do, so that is our derivative. So it's pretty simple if you know the rule. If you don't know the rule, you just really cannot do it. Next one, we have y equals the ln of 4x squared minus 2x plus 9. So we want the derivative, dy dx. And as I'm sure we know by now, we can write that as y prime if we want. I'm just using dy dx. It doesn't matter. Okay, so the derivative of this whole thing is going to be the derivative of what's inside divided by what's inside. So the derivative of 4x squared minus 2x plus 9 is going to be 8x minus 2. And then you just divide that by what's inside, and that is your derivative of that whole entire thing. And one more for this particular type of example. We have the ln of x times e to the x. So this one is going to be, it's going to start off the same way. We have this function inside of here. It's x times e to the x. So it's going to be the derivative of that divided by that itself. So the derivative of x e to the x, we actually need product rule. So that's going to be first. So the first one, which is x, times the derivative of the second. The derivative of e to the x is just e to the x, plus the second times the derivative of the first. Derivative of x is 1. And that's the product rule. And now we put that over the little function itself, x e to the x. And now we can just clean this up a little bit. So this is going to be, looks like we can actually factor out an e to the x in the numerator, and then we'd be left with x plus 1 divided by x e to the x. And I did that because I saw that these were going to cancel. E to the x divided by e to the x cancels to 1. And we are left with x plus 1 over x. And I'll stop simplifying right there, and that's our derivative. Okay, one more example here. The function f of x equals ln of x over x has a relative extreme point for some positive x value. We want to find that point and determine whether it's a relative max or a relative min. So as usual, when we're trying to find these relative extreme points, we take the derivative, set it equal to 0, and solve for x. So the derivative here, the derivative f prime of x, we need to use the quotient rule. So that's going to be low times the derivative of the high minus the high times the derivative of the low. So we get x times 1 over x minus ln of x times 1 all over low squared. So you have to remember the quotient rule. You know that low means denominator, high means numerator. And let's simplify this first. That's going to be 1 minus ln of x over x squared. So that is the simplified version of the derivative. And now we're going to go ahead and set f prime equal to 0 and solve it. So we're going to set this equal to 0, 1 minus ln of x over x squared, set that equal to 0, and solve this for x. So solving this for x now, we have to know that this is a simplified fraction. We can't cancel any common factors here with the numerator and denominator. So we have to set that numerator equal to 0. The only way a fraction equals 0 is if the numerator is 0. And now we solve this for x. So let's add ln of x to the right. We get 1 equals the ln of x. Now to get x out of that ln, we have to do that inverse property. I believe we did it earlier in the semester, and we also did it in the last few sections. We have to essentially raise base e to both sides, and that would be base e to the first power equals e to the ln of x. We didn't really think of it that way. We just simplified it to this right here. So we went from logarithmic form to exponential form. Remember, that's this little conversion right here. And we did that because now x is by itself. That gives us x equals e. So we know x equals e is when the derivative is equal to 0. We have to see if it's going to be a relative max, relative min. We know it's one of them because the problem told us it was one of them. So let's go ahead and set this up. And I'm going to do it using the first derivative test. If you remember, you could check this using the second derivative test also. They tell you the same thing. It tells you whether or not it's a max or a min. So we have our 1 point e, and this is going to represent f prime down here, and this will represent f up here at the top. And we need to choose test points to the left and to the right. I'm going to choose 0 to the left because it's easiest, but actually we can't choose 0 because this is ln function. Ln is for only positive x values, so let's choose 1, and let's choose 4. So we just chose a number to the left of e, to the right of e, that was in the domain of the function itself. And what we have to do here is we have to evaluate f of 1, f prime of 1 and f prime of 4. And we have to see whether or not these are positive or negative. So if we evaluate f prime of 1, here's the derivative all the way back up here. If we plug in a 1 here, we end up getting a positive number. I'll leave that to you guys to check. We end up getting a positive number. And if we evaluate f prime of 4, we get a negative number. So positive for 1, negative for 4. That means f is increasing, and then f is decreasing. So since it changes from increasing to decreasing, then that means it has to be a relative maximum value. And we can see by the graph that it is a relative max. Obviously, we don't always have the graph right in front of us, but I put it on here just so we could have a visual. And for the y value, for right here, 1 over e, I plugged in our x value into the function to get the y value, so I evaluated f of e. Okay, and then for the last thing, not going to go too much into this, but this is just the derivative of the ln of the absolute value of x. So we know that the ln of x graph looks like this right here, the right portion of it. But if we take the absolute value of x, that means we can actually use negative values, because if we take the absolute value of a negative, it becomes positive. So that it ends up looking like this for y equals ln of the absolute value of x. And the derivative of the ln of the absolute value of x is 1 over x, just like we would expect from what we did at the beginning of this section. But the only difference here is that x can be any number other than 0, including negative numbers. Okay, so just keep that in mind. We might be coming back to that. Okay, so that is it for this section.